Hi, honors physics students. Today we're going to talk about spherical mirrors. And what a spherical mirror is, that is a mirror that has a shape that is a portion of a sphere. So that means that the surface of the mirror is consistently curved all along its reflective surface. So that is what a spherical mirror. We're going to look at two different sorts of spherical mirrors. The first one we're going to look at is a concave mirror, and that is for the curved surface of the spherical mirror. The reflective side of the mirror is on the surface that's the inner curve of the mirror, right? So it's on the inside of the curve. We're also going to talk about convex mirrors. Convex mirrors are mirrors where the reflective surface is on the outside of the curve. And these two shapes of mirrors are what we're primarily going to be looking at. This, what you see in the bottom right hand here and in your notes, is an example of a convex mirror, meaning that the reflective side is on the outside of the curve. So let's take a look at what a concave mirror looks like. This right here shows a concave mirror. You can see that there are rays of light coming in from the left of your screen, and when they interact with the surface of the mirror, each one of those reflects from the surface of the mirror, and they converge at some point in front of the mirror. So a concave mirror, each one of these rays of light follows the law of reflection. So the angle in is equal to the angle out, and then when it converges at that point, we see that out. If we contrast that with a convex mirror, this has the reflective side on the outside of the mirror. So now when each one of these rays of light that's coming in from the left strikes this mirror surface, each one of them reflects off the mirror surface using the law of reflection, but they converge or they diverge after hitting the mirror. Because they're spreading out after they hit the surface of the convex mirror, the focal point is always going to end up behind the mirror. And again, you saw this at the bottom of your notes, the convex mirror. Here you see the reflective side on the outside. If you look at the top of the next page, we have some diagrams down below that show the concave and the convex mirrors I just showed you. And up above, I want to define what the principal axis is. The principal axis is an imaginary line that goes right through the center of the mirror. And if you look down at these diagrams, you can see that the principal axis is labeled on each of them, and it's dead smack in the middle of both of the mirrors. Whether it's concave or convex doesn't really change that aspect of it. Now you'll see a bunch of notation on here. You'll see an F and a C. There's an R down there. So I want to define a lot of the notation about mirrors, and we're going to use the same notation in mirrors and lenses basically for the rest of our geometric optics notes. So the first term I want to talk about is what focal point is. Focal point is the point where all the reflected rays converge at. I'm just back on that last slide one last time, because if you're looking at both of these diagrams, you see the focal point, which is the capital F labeled on the diagram. And in the concave example on the left, the focal point is in front of the mirror, meaning it's on the side that has a reflective surface. If you look at the convex mirror, the focal point is behind the reflective surface. So in each of these mirrors, they both have focal points. The focal points is where all the rays converge once they're reflected. But the convex mirror is slightly different in its focal point because the light of the rays themselves does not pass through the focal point. They just all line up with the focal point. So when you're looking at a ray diagram like this, this is the capital F. The lowercase f is used for the focal length. That is the distance between the mirror and the focal point. So we put the F when it's on the diagram. We're identifying the point. If we want to look at the focal length and look at it from like a mathematical perspective, we also use that same F. We just make it a lowercase instead of an uppercase. I said that each one of these mirrors has a radius, or is a section of a sphere, almost like someone took a full sphere and sort of cut it on some plane and then silvered it. So we have the same radius of a sphere, even though it's not continuous in a full sphere. But the radius that's on the surface of the sphere does have some curvature center. So if the full sphere was there, it would have a consistent radius. The radius that the curvature of the mirror experiences is given by the capital letter R. And then we also have, so that's the mathematical term. If we talk about the center of curvature, that's the point, if we're looking at a ray diagram, where the center of curvature is. So you can see the center of curvature on on both of these diagrams, and you can see the focal point on both of these diagrams. The center of curvature and the focal point will always kind of be on that principal axis. So when we talk about the principal axis, it's always hitting the dead center, middle of the mirror. So the focal point and the center of curvature both will fall on that point. If we want to compare the radius of curvature and the focal length, we can look at this mathematically, because the focal length will always be half of the radius of curvature. So if you're looking at the diagrams, you'll always see that the focal point F is going to split the distance between the center of curvature and the surface of the mirror. The center of curvature is not always identified on the mirror. However, a focal point always is. So now that we've talked about how curved surfaces that are used as mirrors still reflect using the law of reflection, and that whether it's on the inside or the outside, that the rays are going to converge either in front of the mirror or behind the mirror. But I want to talk about some simple rules for drawing the rays. If you look at this diagram down below, you can see that we have rays here. And every time a ray bounces off the mirror, and you can follow the ray by the arrows, you see the rays are coming in from the left, and then they strike the mirror, and then the rays leaving, some of the rays, all the curved ones, leaving the surface of the mirror, all have arrows on them as well. So you can see they come in, strike the mirror, and then each one of them independently bounces off the mirror. All the rays come together at one point, which is the focal point. I want to talk about how we can use a series of rays drawn to identify where the focal point is. Because if you looked at just one reflection, you wouldn't know where it would be meeting the other reflection. So we have 3 different rays that we're going to talk about, and each one can be used to identify where the focal length or the focal point is on the mirror. So let's talk about this first ray. Ray 1 is drawn parallel to the principal axis and is reflected through the focal point. When we draw rays, we're going to draw them from some point on the object whose image is reflected. We have to choose a position on that object, and we can identify through multiple rays where the position of that object will end up in the image, and then just identify that between that location and the principal axis. So this ray 1 is drawn from an object, and I'm going to show you this in a simulation. And so right here, you're looking at a simulation, and instead of using an object, what you see is the arrow on the left. I could change that to a candle or an arrow or some letters. But whatever scenario that I'm talking about, if we want to figure out, we have a mirror in the middle, how the rays of light are going to bounce off the mirror, reflect off the mirror, and then form another image at a focal point, we're going to use rays. So the first ray we talked about comes in parallel, and you can see this one is coming in parallel. It reflects off the mirror, and it comes and passes through the focal point. Somewhere along the line of that reflection, the image is going to form. You can see the image is already formed back here in this diagram of the smaller inverted candle. So that's our first ray. Comes in parallel, bounces off the mirror, and then it has to move from the mirror in line with the focal point. So let's look at our second ray. Our second ray is drawn to the point where the principal axis meets the mirror, and then it reflects from that point as if it was a flat mirror using the law of reflection. So if we look at that second ray, this one, we're starting the ray at the top of the candle, because when we did our ray 1, we started at the top of the candle. So we always start our rays at the same point on the object. We're going to start this ray at the top of the candle. That ray is going to come in. It strikes the mirror right where the principal axis meets it, and then it reflects off as if at that point it was a flat plane mirror. So here we can see we have a ray, and if we turn our ray 1 back on, where it reflected off in this line, and we combine it with our second ray, we're seeing that the rays are converging at some point that is representative of where the candle top is. So we started at the candle top of our object, and now they're converging where the candle is for the image. Looking at our third ray, ray 3 is drawn through the focal point, and then it reflects parallel off of the principal axis. This is the inverse of ray 1. So ray 1 and ray 3 are more or less the same ray, just like one is going to the one goes parallel to the mirror and then through the focal point. The other one goes through the focal point and then parallel out from the mirror. So let's take a look at this one. Here we're starting at the top of the candle, and then we draw a ray right through the focal point. And then when it strikes the mirror, it reflects off parallel. And if we look at all three rays together, right, we started with ray 1, then we drew ray 2, they converge. We draw ray 3, it again converges. This is how we locate an image when we're looking at the geometry of a mirror. So what I want to do is on your next slide, you have a link to the simulation that I was just using. Just take a moment and play with it as a mirror. You can change the option between mirror and lens, but just look at it as a mirror. When you're looking at it as a mirror, if you pull your candle to the right of the curved surface, what you'll see is that the rays now are bouncing off. They're all in line still, and the image is where all the lines of them meet, but they meet behind the mirror. This is a virtual image. We talked about virtual images. So while you're playing with this, you can look at concave mirrors by staying on the left and convex mirrors by staying on the right. So go ahead, try that, and then we'll come back together and finish up this packet.